Welcome to Maths with EJD. In this video, we continue with the scientific computation with Python, with a series we've been looking at. And today, we'll be considering the SciPy.Integrate module. Of course, as the name implies, the SciPy.Integrate module provides several functions for performing integration, and which is integration is a fundamental operation in numerical analysis and scientific computing. Of course, integration is the opposite of differentiation. I have done a whole series on calculus where I talked about functions, where I talked about differentiation and, of course, integration. So if you are interested in the theory of integration, you may want to revisit that. I'll try to put that in the description box so you can check down there to see the link to the playlist on basic calculus, and then you can jump to the integration part in case you need to understand the basis. So here we are focused on the computing part of all of that. So let's go. So under the SciPy.Integrate module, right, we are looking at all the various capabilities of that. And the first thing we are looking at is the single integration. That's you just integrating, with respect to one variable. For instance, okay, of course, for that, you need the quad function. The quad function is used for integrating a single variable function over a fixed interval. For example, you want to integrate f of x equals sine x from 0 to pi. Of course, uh, to integrate f of x equals sine x, right? If you integrate sine x, of course, differentiate sine x, you get cos x, right? But if you differentiate cos x, you get minus sine x. So that means that if you integrate sine x, you get minus cos x. So if you now integrate, put 0 to pi, right? That pi is 180 degrees. So that's like minus cos, right? That's minus cos pi minus cos 0. Minus cos pi is like cos pi itself is minus 1. So that's like minus minus 1. Then cos 0, I think, is 1. So that's like is that 1 minus 1 or something? So let's see that. So this is the code for that. So here from SciPy.Integrate, you import quad, which is the function you're going to use. Then you need to do some numerical stuff. So you need numpy. So okay, let me put the line numbers, all right, for easy referencing. So in line 4 now, you are defining the function. So the function is sine x. So you say f equals np dot sine, all right, because you get the sine function from the numpy library. So then in line 8, you're actually performing the integration, and then that will give you the result of the integration and the error. Of course, the sine curve goes all the way to as long as you want it to go. So as a result of that, you are only going to get the result for 0 to pi, because sine can go from 0 to, in fact, maybe from minus infinity to infinity, right? But here we just want to take that part. So it means that there are some portion that will be error, right? So, and that's exactly what's happening in line 8. So we get the actual result of integrating from 0 to pi, and then we get the error, and then the actual work is happening here. So you use the quad function on the function you have defined as f, then from 0 to pi as expected, and then in line 10 you're printing the result and the error. So just run this and the result jumps out at you. So here the result is 2.0. Of course, just like I said before, that's like minus cos x, right? That's minus minus 1, that's 1. Then minus cos 0. Cos 0 is 1. I guess, okay, yes, I get it now. So you have minus cos x, right? So if you put the minus out, so you have minus and you have cos x. So that's cos 0, cos pi, which is minus 1, then minus, okay, if you take the minus out, right? So you have cos pi plus cos pi plus cos 0, if you take the minus out, because normally that should be like minus cos x. So that's minus cos. Well, I mean, the result in the end is something like minus 1, minus minus 1 plus 1. And that's why the answer is 2. And the error is all this that thing you get. It's very small, so that means it's not a bad one. So that's single integration. When you talk about double integration, here you use the function double quad. So that means you are integrating over the x and y axis. So this is like a three-dimensional thing, so to speak. So here, you are using the double quad function, which is used for double integration of a function of two variables over a rectangular region. So, for example, you want to do f of x equals x dot y over the region 0 less than, over 0, 1, that rectangle. In fact, yeah, that's a rectangle, 0 to 1, 0 to 1, like that. Or maybe even like a square, right? Because the length and breadth are the same, so to speak. So we have the code here again. So now you have to import DBL quad, and then you define the function. So we use the define function thing. So you have f of xy, which is x times y, because that's x dot y. And in line 8, the work is happening again. So perform the double integration. So you do the double quad. So the function, you're doing that over 0, 1 for the first part, from 0 to 1, so you have lambda x, and from 0 to, and again you have from 0 to 1 for both lambda x is 0 and lambda x is equals 1. That means when x is 0 and when x equals 1, you are integrating that function over that range. That's for x equals 0 to 1, x from 0 to 1 and y from 0 to 1. And this is how that is represented in line 8. So you just run this and you get your results. So of course, just like you know already, the notes is always available. So you can check the description box. You find the link to the notes. So before you even start following this, probably you should even get the notes so you can follow through. And of course, after each one, you can copy it out and change the function and update the code and see how all of that works. Okay, so now we go to triple integration. This kind of thing happens when you're dealing with surfaces and volumes, especially in when you're dealing with some kind of vectors like that, when you're dealing with geometry, the surfaces of the earth and things like that. So the triple integration function is actually TPL quad, which is used for triple integration of a function of three variables over a rectangular region. So now we are talking about x, y, and z, right? So you have defined the function in line 4 and 5. You have x times y times z. Then perform the triple integration. So you get the result and the error. So triple quad f from 0 to 1. So here we are assuming that everything is from 0 to 1. So you have lambda x 0, lambda x 1, lambda xy 0, lambda xy 1. So it's like for both x and y. So you have all the whole thing from 0 to 1 all the way, and then you run that and you get that result. Okay, so we move on to numerical integration using trapezoidal rule. Trapezoidal rule is a technique for numerical integration. So numerical integration using trapezoidal rule. So the trapezoidal function is used for numerical integration using trapezoidal rule, which approximates the integral of a function given discrete points, right? So here we are using discrete points. And that is why in the example, you can see that the number of points has to be specified. So if you want, and the more the points, the better the result, right? I'm going to demonstrate that with this particular code. So again, you import traps from SciPy.Integrate, which is the module we are considering. Then in line 5 and 6, you define the function. So x is, so of course, the point we need now from 0 to 1, that's 5. And then y is x squared, f of x is x squared. Then you perform the integration, which is so the result is just a variable name. So you have traps y comma x, and you just get the results over 5 points. Now, if we do, let's take, just like I said, the number of points you take determines the accuracy of your result. So if I do this now, and instead of taking 5 points, and I'll take let me take 50 points, that's a lot, right? See, the results will be finer than this. So you can see there's a bit more difference in the result. That means this result is more reliable. So here, instead of 5 points, I'm using 50 points. 50 points. So what that means is that you're dividing this interval 0 to 1 into 50 equal parts. So it's like 1 minus 0, 0 divided by 50. So you're moving 1 over 50 steps like that. But in the first case, you are doing 1/5. That's 0.2 in each case, whereas this is 0.02. So because of the fineness of the points, the result tends to be better like that. So the more the points you choose, the better for you. Okay, so once to solve the same problem using the numerical integration, doing numerical integration with Simpson's rule. Generally, Simpson's rule seems to be I think it's usually more accurate or something. So let's see. So the Sims function is used for numerical integration using Simpson's rule, which is more accurate exactly than the trapezoidal rule for certain types of functions. So we want to integrate f of x equals x squared over the interval 0 to 1 using 5 points. So here, now with the same 5 points, you see the result is like 0.33333, like you can see already. Of course, we can easily verify this analytically. So integrate x squared, that is 1/3 x cubed, and then put 1. So that's like x 1 cube minus 0 cube. That's 1/3 in short. So you can see the result, it should actually be 1/3, which is 0.33333. So even with Simpson's rule, now you can see it's perfect, this way. So Simpson's rule is way better. In fact, if I change it to like 50 points, maybe it doesn't make much difference because maybe it makes the result even worse or so, because normally we expect it to be like 0.33333 like that. All right. So comparatively, Simpson's rule is better than trapezoidal rule. It's more accurate, especially the way it's even defined. So you can just Google online to see the formula for the Simpson's rule. If I had remembered, probably I would have written out the equation so you see what it looks like. But any day, anytime, Simpson's rule is better than trapezoidal rule. Okay, so we go to solving ordinary differential equations. Things are getting more interesting. Now, most of the things that happen in life, like if you want to represent things, how things change over time, differential equations are very good for representing them. So ordinary differential equation is when you're comparing something with when you have one dependent variable with respect to one independent variable. But if you have one independent variable with more than one independent variable, then you have to talk about partial differential equations. So let's say that for this now, solving ordinary differential equations, the ODE int function is used to solve ordinary differential equations. For instance, we want to solve the ODE, the y dt equals minus 2y with the initial condition y of 0 equals 1. That's when x is 0, y is 1. Of course, this is simple enough to solve using separation of variables. So we can actually get the analytical solution for this. But of course, sometimes things get complicated and you have a problem whose solution is even bigger than this problem, whose solution is more complicated than the problem itself, right? That's why numerical solutions are very important. So here are some visual, of course, the results you're going to get is when you solve this kind of function, right? When you solve this kind of equation, you're going to get y, and y actually can take different variables. And that is why it is important to visualize it instead of just seeing the numbers, coming out like that. Okay. So let's say that okay, of course, here we are using ODINT. Then we need to do some numerical calculations. Then we need to visualize. Now that's what I'm doing Matplotlib. I'm still going to do special videos on all these techniques for visualization, like Matplotlib and Seaborn, which is also based on Matplotlib. So in lines 6 and 7, we define the ODE, the y dt equals minus 2y, like we have. And then here you want to define the interval. Of course, again, we've seen that interval thing that the more the more the points you have, the better the result. So in line 10, we divide 0 to 5 into 100 equal parts. And then the initial condition, that's the initial value of y is 1, okay? And then line 16 is where the actual thing is happening, where you see the function working. All the int, the y dt that has been defined up here, together with the initial condition, and then the independent variable, right? And then, so once that is done in 16, so the result is visualized here in form of a plot. So, of course, from what we see here, the y dt is minus 2y. That means it's a decay function. So it's like something is going down, just like when you talk about uh, decay in physics, like maybe you have a particular element decaying, talking about things like half-life and the rest of them. So you can see that's why you see the plot moving from up and it's going down over time, right? Okay, so you can change the differential equation and see what happens. For instance, what if we have like I was going to solve, okay, let's do this. Let's say we have I do this and I go to a new place and I have this. So what if this is now minus 2 star star? I mean y squared, minus 2y squared. What happens? So we get something. So it's still a decay thing, but it doesn't decay as fast, I think. It doesn't decay as fast. So this one gets to 0 almost around 2 point something, but this one doesn't get to 0. In fact, it's still not at 0 at 5. So what if we extend, say, if you take it to, will 50 be too much? Let me take it to 10 and see what happens in that line. Okay, even at 10, it's still just moving forward towards it. So what if we go to, say, 100? Maybe that's too much, but let's see what happens. Okay, yeah, I guess 200 is way too much. Let's say 50 now. Let's say 50. Okay, so it gets to 0 around 20 something. Let me go to 30 and see, so this decay is slower because of the nature of this, like that. So the decay is slower. So in 7, the 7th one is the adaptive quadrature. So the quadrature function performs adaptive Gaussian quadrature, which is useful for high precision integration. So if you want to do high precision integration, so you can come for adaptive quadrature, and the function to use is quadrature from this SciPy.Integrate module. So here, import numpy as np, you define the function sin x squared, and then you get the result and the error, and you're integrating from 0 to pi in line 9, and then you print. So, you have the result and then you have that error. Okay. So then we also have the Romberg integration. So the Romberg function uses Romberg integration and extrapolation method to improve the accuracy of the trapezoidal rule. So, if you want to increase the accuracy of trapezoidal rule, so you go Romberg. Okay. So here, once we integrate f of x equals ln x from 1 to 2, like that. So you have from SciPy import Romberg, and then you define the function log. Log comes from numpy, so we need np.log x, and then you do the actual work in line 9. That's Romberg of the function from 1 to 2, and then you get the results like that. Okay. So you can change the function and see what happens. Okay, here we get things get more interesting. We have systems of equations. So here we're talking about solving initial value problems for ODE systems. You can get this kind of ODE systems by probably if you have like a higher order differential equation, like a second order, like you have y prime prime equals something. So there's a way you can break that down to get two systems like this, or you can actually be presented with systems of equations. It can even go as far as like you have a system of 10 equations like that. So here, you want to solve the initial value problem using the function solve_IVP, which solves the initial value problems for systems of ODEs with more flexibility and options compared to ODE-int that we've been talking about. So the example, solve the system of ODEs. So you have dy1 dt equals 0.5 y1. So here you have two things happening together, and they are defined by this evolution. So they are joined together. So you can see dy1 dt is minus 0.5 y1, whereas the y2 dt is 4 minus 0.32 y2 minus 0.1 y1. So you can see y1 happening in y2. So this is a coupled system of ordinary differential equations. So it means they evolve together, right? They evolve together. So this is the kind of equation we tend to use a lot when we talk about things like SIR equations, SIR models, for epidemics, for disease spread. So, and of course, we need initial conditions. Y1 of 0 is 4 and y2 of 0 is 6. So, of course, you have this whole thing. So you need solve IVP from SciPy.Integrate. Then you need NumPy, you need matplotlib, like that. And then, of course, you define the system of equations. So here we have only 2. So for y1, we have y of 0. For y2, we have y of 1, and all of that goes to in line 7, 8, 9. So it's returning. So you need the function to return dy1 dt, dy dt1, and dy dt2. So if you have more than 2, you just keep defining them as you go on. Then, of course, you need the time span. Do you want it from 0 to 10? You can always change the time span to see what happens to the system. And, of course, you need the initial conditions now. So you have y1, y2. y1 at the initial point is 4. y2 at the initial point is 6, just like we have in this problem. Then you now solve the ODE system. So you have solution, solve IVP, So you put the ODEs that you have defined here, ODEs, then the T-span, that's the time over which it's happening, and then the initial condition. And then the method you're using is Runge-Kutta 45, RK45. There's something like this also in MATLAB. And then you're evaluating from 0 to 10 with 100 divisions, which you can also tweak if you like. And then what you have in the rest is the display of the results. So you're going to see in the results how Y1 and Y2 evolve over time. How Y1 and Y2 evolve over time. So that's what happens in this case. Okay, so what if we want to increase the time span to say, like we're going, let's go 100, and see what happens. So this is 100 now, 100 in 100 divisions. So the plot, okay, so you can see the plot flattens out over time. So we can actually, leave it at 10 where it was, so because after some time, like the whole thing just relaxes, and then that's what it is. Then of course this Y1 of T, you can actually change it. If you use LaTeX, for instance, maybe I'll explain LaTeX one of these days so you can see how that goes. So so you have this. Okay, so you want it to appear neatly like a math thing that it is. So you can see it's now like Y1 of T, Y2 of T. So you have all of that happening. Okay, so let's talk about numerical integration for functions with singularities. Singularities means that, there's a particular point where the function is not defined. So numerical integration for functions with singularities, we still use the quad here. So you can see the quad keeps coming up all over. So the quad function can handle integrals with weight functions to improve accuracy around singularities. Of course, I don't even think the weight function is necessary in this particular case. Example, f of x, integrate f of x equals 1 over root x from 0 to 1 using a weight function. You know that this function f of x is not defined at 0. So the weight function doesn't even come to play here because we just have that going. So from SciPy integrate, import quad, and then of course we need numpy. So define the function, and the function is returning 1 over square root of x. So perform the integration, it's just a result error quad. The function f of x, you have the f, and it's from 0 to 1, and you have, so you just run that and you get your results. No big deal. All right. So let me change. What can I tweak? Maybe I want to tweak, say, okay, we can't do minus. Let's go, say, from 0 to 10 and see what happens with this. Okay. So the result is now 6.32 something, and the error is even the error seems bigger than in the other case. So it's like the wider the interval, the higher the error. Of course, it's still small, but it's a little bit bigger than what we had. So let's talk about integration with infinite limits, still using quad. So the quad function can also handle integrals over finite intervals, over infinite intervals, like you're moving from 0 to infinity. So let's integrate f of x equals 0 to minus x squared. I think this is called the is it the Gaussian equation or something like that? I'm not sure now. So import quad again. So define the function. So exponent of minus x squared. So this e raised to minus x squared is how you define that. And then you're integrating from 0 to infinity. Of course, you can't just use infinity. You have to call it from numpy. And then you print the result. And that's what you get. Okay. So that's that. Okay, so let's compute cumulative integrals. You can also do cumulative integrals. So the COMTRAPS function computes the cumulative integral of an array of data points using the trapezoidal rule. Example, compute the cumulative integral of f of x equals sine x over the interval 0 to pi. Of course, we already know there's a particular format we follow. Import everything you need to import, and then in this case, we need to define the interval, right? From 0 to pi. Of course, you can choose the number of divisions you want, and the y itself is actually sine x. So then in line 10, that's where the show is happening. So you have cumulative integral, which is a variable name, equals COMTRAPS, then y comma x, and the initial value is set at 0. You can always tweak that, but I mean, it's 0 here, so maybe that's better. And then we can visualize using all this. So I'm not bothering so much about this visualization part because I think I'm still going to do video explaining how all these things work. So when you do that, you have the original function sine x, from 0 to, you have that happening like that. And then the cumulative integral, goes something like that. So you can see that it is just an estimation. So there'll be a bit of error. And finally, we come to integration of multivariate functions over a general region. Here you talk about n quad, right? So the n quad function allows for the integration of multivariate functions over a more general region than the the double quad and triple quad. Okay, I should highlight this. I just say double star underscore double star, and then I say double star underscore, and then underscore double star, and that goes, and we have this. Okay, so here we want to integrate f of x, y equals e raised to minus x squared minus y squared over the region where x and y range from minus infinity to infinity. So we get the n quad out, that multivariate quad, like n-dimensional stuff. So you define the function exponent of minus x squared minus y squared, and the limit is minus infinity to infinity for each of x and y. And then the actual show is happening in line 12, where you do n quad, then f comma limit, and you run that and you get your result. So it's been such a sweet adventure. So you want to, don't forget, the notes are available from the link in the description. So it's always nice to download the notes and follow, so you can do this hands-on. And the best way to learn is tweak. So once you run one and it works, so change values, tweak something, change something, satisfy your curiosity, and you might just learn something new. So we've come to the end of this video. Of course, if you have not subscribed, you'll be missing a lot going forward. So you want to subscribe and hit the notification bell so you can get alerted anytime a new video is released. Of course, feel very free to comment, like, and share with others, because this is, I've been getting a lot of feedback that this is really helping a lot of people to get a hang of scientific computing using Python. Thank you so much for listening. See you in the next video.